Okay, now we are going to look at what is called the absolute maximum shear stress, which is the largest shear stress acting at a certain point, at a particular point in an object under loading. Okay, now this diagram here, the first diagram, shows a three-dimensional stress state for an element at a point. Now, on each face, we'll find one normal stress and two shear stresses acting on that single face. Therefore, if we look at the three-dimensional element, then we have three normal stresses in the direction of y, z, and x, and also three shear stress components in the three planes xy, xz, and yz. Okay, so we have three shear strains. In our case, we only cover plane stress condition. Okay? For plane stress condition, we are looking at a situation where we rotate this stress element and we can get three principal stresses. We can rotate the stress element such a way that we will find we have three principal stresses on the stress element. We have sigma minimum, sigma intermediate, and sigma maximum. So in this direction, we can find three principal stresses, and we call this a triaxial stress state. The 3D stress element, which is oriented at x prime, y prime, and z prime, as shown on the top left. Okay, this stress element has principal stresses acting on the three surfaces. We have sigma intermediate, sigma minimum, and sigma max acting in the x prime direction. Now, this three-dimensional stress element, if we look at it from the x prime direction, we will see the figure on the right, on the top right. Now, that will show us the plane, the blue plane, which is being looked at from x prime direction. And then we can see sigma intermediate and sigma min. If we take a look at the three-dimensional stress element from the y prime direction, we will see sigma minimum and sigma maximum acting on the stress element. That is on the plane x prime or z prime. And if we take a look from the top or from z prime, we will see the 2D stress element at the bottom right, which is on the x prime y prime plane, which will give us sigma max and sigma intermediate. Okay, so these three diagrams on the right, each of them is similar to the plane strain diagram that we have done before. So for each plane, y prime z prime or x prime z prime or x prime y prime, each one can be analyzed using Morse curve. We can draw Morse curve for each plane, and what we then have are the three circles as shown in the Morse curve, right? So here is sigma, and the vertical axis is tau. Counterclockwise is positive. Okay, and then we can draw as usual. We can plot the three principal points. sigma max, sigma internal, and sigma min, and get the 3 circles. Now for each of the circles, we can find its own tau max, right? We can find the maximum in plane shear stress. So the in plane shear stress for the blue circle, the light blue circle will give us tau max for x prime, y prime. Okay. For the blue circle, now it will give us, sorry about the crooked line, it will give us tau max x prime, tau max y prime, z prime. That is the maximum in plane shear stress for the plane y prime, z prime. While the yellow circle will give us the largest shear stress. The yellow circle will have its own in plane shear stress, tau x prime, z prime. And since it is the largest between the 3 circles, it is also the absolute maximum shear stress. So if we are looking at if we are looking at x prime, z prime plane as our analysis plane stress plane, then the maximum in plane shear stress is also equal to the absolute maximum shear stress. However, if our plane stress condition that we do is x prime and y prime, then it is out of plane. The absolute maximum shear stress is out of plane. Okay, for plane stress condition, we only have 2 principal stresses, right? For example, if we have only sigma max and sigma intermediate as our value, okay? And the third one is out of plane. So the third one is 0, okay? The third one is 0. So we have maximum and intermediate value. So that is in plane, in our plane. So if these two, intermediate and maximum, is our plane, and we draw the more circle for the 3 planes, okay, our plane is maximum and intermediate. That is our 2 plane stress condition. Okay, so we are talking about this circle here, which is not the largest circle. Okay, it is not the largest circle. That is the plane stress circle. The other 2 circles is formed because we know that sigma min is 0. That is the third point, but it is an out of plane direction. Meaning, this smallest circle, right? The smallest circle and the largest circle are both out of plane. And the absolute maximum shear stress will be from the largest circle. Okay, sorry, that point there, right? Now that is the largest circle, therefore that is the absolute maximum shear stress. Whereas this value here and this value here are both maximum in plane shear stress for its own plane. But when we talk about our own plane, now this will be the maximum in plane shear stress because we are talking about plane stress condition. Okay, this is out of plane. This is also out of plane, but it's the largest, so it's the absolute maximum. In other words, okay, for this condition, the absolute maximum shear stress is equal to sigma max over 2 if both our in-plane principal stresses are positive, right? So if sigma 1 and sigma 2 are both positive, then absolute absolute tau maximum is equal to sigma 1 over 2. Okay. Now we have another case where one is positive and one is negative. In this case, sigma max or sigma 1 is positive, positive, and sigma 2 is negative. This is minimum stress. This is maximum normal stress or principal 1, and this is minimum normal stress or principal 2. Now if one is positive and the other is negative, what we then have is this graph here. That is our in-plane principal stresses. Sigma max, sigma min. While the sigma intermediate, which is equal to 0, is out of plane. And so our in-plane circle is the largest circle, right? And our in-plane maximum shear stress is also equal to the absolute maximum shear stress. So the absolute maximum shear stress is equal to sigma max minus sigma min over 2, which is also equal to the in-plane maximum shear stress. Okay, let's take a look at an example here. Now we are given this problem here. There's a bent bar fixed at point A here with a single load P horizontally in the minus Z direction, right? Acting at the free end D. Now it says here, determine the normal and shearing stresses on an element at point H. Now here is point H there, the red dot. Okay, that red dot is point H. And point H have sides parallel to X and Y axis. So when we take the stress element will be parallel to X and Y. So our stress element will be something like that. And we look at it from Z direction. Okay, we look from Z here. Okay, and we look at the stress element right perpendicular onto the face. Okay, and then it asks us to find the principal planes and principal stresses. First, you find the element, stress element, due to the loadings, and then you find the principal planes and principal stresses. So first, we have to determine the equivalent force couple system at the center of the transverse section passing through H. We take a section passing through point H. Alright, then we have to determine the force and moments acting at that cross section. Then we evaluate the normal and shearing stresses at H, and then from there we can determine the principal stresses and planes. Okay, so if we look at the loadings, we know that the single force acting at point D will also produce a shear force here, the shear force acting in the same direction as the force at D. Okay. At the same time, it is also applying a torsion to this component here. So we have a torsion. And then we also have a moment. Okay. a moment about x. So we have this here. The moment about the x-axis is bending this vertical part of the component, bending about the x-axis. So if we take a look at this tree, we will find that when we take shear, transverse shear, now this is acting at the top or bottom part of the cross section. Therefore, the shear due to transverse shear is 0, right? Due to transverse shear is 0 effect. So there's no effect from this force on that component. Sorry, on the element at H. If you take a look at the moment, now it's bending clockwise about x if we look from x. Therefore, we know that over here, H on the top surface, we will have a tensile stress. Okay, so we have this stress here, and that comes from mx, right? Moment about the x-axis. So it's a bending moment. And if you take a look at the torque is turning counterclockwise about y-axis. Okay, it's turning counterclockwise. Therefore, on the top surface here, it is going to the right. If we look from Z, okay, we are looking from Z, from the surface, it's moving to the right. So it's moving to the right on the top surface. And this is due to T, right? And sigma x is 0. There's no force or loading which is applying stresses in that direction, in the horizontal direction on the vertical surfaces. So automatically this is equal to 0. Okay. So if we evaluate the normal and shearing stresses, sigma y is due to the bending mx. Therefore, we have mc over I. M is 1.5 kilopounds inch. The furthest distance, which is the radius, is 0.6 inches. And I, second moment of area of the circle of the cross section about its neutral axis is pi d 4 over 64 or pi r 4 over 4. So we use this equation here to find the bending stress, which is 8.84 kilopounds per square inches. So there is that value there for sigma y. And it's positive, therefore it's in tension. Okay. And tau xy, the shear is due to the torque T, right? And the torque is 2.7 kilopounds inch. The radius, largest radius, is 0.6 inches. J is the polar second moment of area for the cross section, which is a circle. So we have pi d4 over 32 or pi r4 over 2. And if you evaluate that, you will get tau xy is 7.96 kilopounds per square inches. So what we then get is we get this first stress element. So now this stress element shows us that it has sigma y, tau xy, and 0 sigma x. Sigma x, you don't have any values. So if you don't show this, it's okay because it's already 0, right? Okay, now it says determine the principal planes and calculate principal stresses. If you use equation, you just use the basic equation straight away. Tangent to theta p is equal to 2 tau xy over sigma x minus sigma y, right? Which then gives you 2 theta p is minus 61 or theta p is minus 30.5. That is the first angle. The second one is 90 degrees to that, so you can add 90 degrees to get 59.5. Okay, that is the plane. So now we know that the plane is negative angle, meaning is rotating clockwise. So from X, this is our reference, it rotates clockwise 30.5, right? From our principal stress equation, we can have then this equation here, sigma max or minimum, sigma 1 or 2. This can be 1, this can be 2, right? Sigma x plus sigma y over 2, which gives you the average normal stress, plus minus square root of sigma x minus sigma y over 2 square, plus tau xy square. Now this will give you R, right? Therefore, if we replace the values inside the equation, then solving this equation, we get sigma max is 13.52 kilopounds square inches, and sigma min is minus 4.68 kilopounds per square inches. Okay, that is the minimum stress. And then we can put it on the stress element. However, remember I told you, you should not just assume that on this plane it is negative, the smaller value, the minimum value, and on this plane is the larger value. The best is for you to test by using the general equation that we had, which is sigma x prime. Okay, so we have sigma x prime is sigma x plus sigma y over 2 plus sigma x minus sigma y over 2 cos 2 theta blah 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 until the end. Use this equation with theta is equal to minus 30.5, okay, minus 30.5, and then we can get to know whether on this plane here, it is going to be uh, the smallest minimum or the largest or maximum normal stress, right? This is another example. It says here the point on the surface of the cylindrical pressure vessel is subjected to state of plane stress. Determine the absolute maximum shear stress at this point. Then it gives you that's the pressure vessel there, and there is the stress element for the question, okay, which is from the pressure vessel. So it says if that is the point on the pressure vessel, we take it out, then we have this plane stress condition. Now, don't ask what is the dimension of the pressure vessel, what is the pressure acting on it, and so on. Because if you look carefully, this diagram at the bottom of the stress element or already give you the values for the stresses, okay, 32 and 16. Now, if you look carefully, there's no shear, right? There's no shear stress. Therefore, these two are the principal stresses. Okay, so we have two principal stresses here. The third one will be 0. Okay, the third one will be 0. So we can then plot on Mohr circle. If we draw the Mohr circle graph, we have sigma 1 is given to us, right? 32 megapascal. Sigma 2 is also given to us, 16. Okay, sigma 2. And the third stress is 0, of course. It's always 0 for plane stress condition. So the third point is here. Now, we can see that our in-plane circle is the one between sigma 1 and sigma 2. That is our in-plane circle. So our circle is the smaller circle. Okay, the one on the right, right? And the other two, the smaller circle on the left and the largest circle in Morse circle diagram, are both out of plane. So our maximum in plane shear stress is this one, which is smaller. So that is tau max. In our case, we can call it x prime, y prime, or just in plane. Okay. Sometimes you write that, or sometimes you just write in plane. So everyone knows that maximum shear stress is in plane. Right. The largest will be down here. That is the largest shear stress because that's from the largest circle. So that is the tau max absolute. Okay, or absolute max, whatever you want to write. Right. So from this question, we can find that tau absolute maximum will be 16 megapascal. And the average normal stress is equal to sigma 2 is equal to 16 megapascal. Okay. Now it says there also you can use direct application of the equation that we obtained earlier to find the value. So remember both our in-plane normal principal stresses or normal stresses, sigma 1 and sigma 2, both are positive. Therefore, if you look at what we have derived, it says tau absolute maximum is equal to sigma 1 over 2. So we still get the same thing, which is 16. Right. By comparison, the maximum in-plane shear stress can be known very quickly from the Morse circle. We can recognize whether it's in plane or out of plane.